Let us consider an LCR circuit for calculating the power dissipation in the circuit. If the voltage applied across the circuit V is equal to Vm sin omega t, where Vm is the amplitude of the applied AC voltage, omega is the angular frequency of the applied AC at time t, then the current I is equal to Im sin omega t plus phi, where Im is the amplitude of the AC current passing through the circuit and phi is the phase difference between the applied AC voltage and the AC current. We know that in an LCR AC circuit, impedance Z is equal to square root of R square plus XC minus XL square, and Im is equal to Vm by Z. Here, XC is the capacitive reactance and XL is the inductive reactance of the circuit. Substituting the value of Z, we get Im as in equation 1. From the impedance diagram of an LCR circuit, tan phi is equal to XC minus XL by R. Let this be equation 2. And cos phi is equal to R by Z. Let this be equation 3. We know that the power dissipated in a circuit is the product of the voltage and current in the circuit. Substituting the values of the instantaneous AC voltage V and AC current I, we get the instantaneous power P is equal to V into I, or P is equal to Vm sin omega t into Im sin omega t plus phi. Using the trigonometric identity, 2 sin A sin B is equal to cos A minus B minus cos A plus B, or sin A sin B is equal to half cos A minus B minus cos A plus B. We get sin omega t into sin omega t plus phi is equal to half into cos omega t minus omega t plus phi minus cos omega t plus phi. On further simplification, we get sin omega t into sin omega t plus phi is equal to half into cos phi minus cos 2 omega t plus phi. Thus, the instantaneous power P can be written as Vm by 2 into cos phi minus cos 2 omega t plus phi. Let this be equation 4. The average power dissipated over a cycle is given by the average of the right-hand side of the equation 4. Here, only cos 2 omega t plus phi is time dependent. However, its average over an entire cycle is 0, as the average value of a cosine function over a complete cycle is 0. Hence, the average power PAV is equal to Vm by 2 into cos phi. Let this be equation 5. The same expression can be written as Vm by root 2 into Im by root 2 into cos phi. We know that RMS values of the AC voltage and the current are given as Vrms is equal to Vm by root 2 and IRMS is equal to Im by root 2. Thus, average power dissipated, PAV, is equal to Vrms IRMS cos phi. Let this be equation 6. Since Vrms is equal to IRMS into Z, we can write average power PAV is equal to IRMS square into Z cos phi. This shows that the power dissipation is dependent not only on the voltage and current in the circuit, but also on the cos of the phase angle phi between them. The term cos phi is called the power factor for the system. Let us observe the variation in the power dissipation across various AC circuits based on variation in the power factor. If a circuit has only a resistor, it is called a purely resistive circuit. In this case, since the phase difference between the AC voltage across the resistor VR and the current I is 0, that is, the value of cos phi is 1. It implies that the power factor is maximum or unity. Hence, power dissipation is the highest in a purely resistive circuit. If a circuit is purely inductive, then the value of phi is plus pi by 2. That is, the voltage across the inductor VL leads the current I by pi by 2. Since cos pi by 2 is 0, we can see that the power factor of a purely inductive circuit is 0. In other words, there is no power dissipation in a purely inductive circuit. If a circuit is purely capacitive, then the value of phi is minus pi by 2. That is, the voltage across the capacitor, VC, lags the current I by pi by 2. The value of cos minus pi by 2 is equal to cos pi by 2, which is equal to 0. Hence, the power factor of a purely capacitive circuit is 0. In other words, there is no power dissipation in a purely capacitive circuit. The current in a purely inductive or purely capacitive circuit, where the power dissipation is 0, is known as wattless current. In the case of CR, LC, LCR series AC circuits, there exists a phase difference between the AC voltage V and current I in the range of 0 to pi by 2. Hence, the value of the power factor will be non-zero, but less than 1. Hence, the power dissipation in these types of circuits is non-zero. The average power dissipated in an LCR series AC circuit is expressed by equation 6, where the power factor cos phi is equal to R by Z as in equation 3. In this case, the power dissipation is only through the resistor. If the LCR series AC circuit is in resonance, that is, the capacitive reactance XC is equal to the inductive reactance XL, and then we know that the value of tan phi reduces to 0. This implies that the value of phi is 0, and hence the power factor cos phi is equal to 1. Hence, the power dissipation in an LCR circuit is the maximum as the power factor becomes unity. The average power, in this case, is equal to the product of VRMS and IRMS. To improve the power factor of a circuit, we often introduce an appropriate capacitor or inductor to cancel the predominance of the other in the circuit, thereby letting the impedance Z of the circuit get closer to the resistance of the circuit. Thereby, we can have Z equal to R, which implies that cos phi is equal to R by Z, equal to 1, which is the power factor at resonance. This is beneficial in many industrial applications. For example, when the distance is large, power is transmitted at very high voltages in order to minimize dissipation. This is so because a higher voltage implies lower current and subsequently lower power loss. The phenomenon of LC oscillations can be observed when a charged capacitor is placed in series with an inductor in a circuit. Consider a fully charged capacitor with plate A charged positively and plate B charged negatively, connected to an ideal inductor of inductance L. When the circuit is closed, the capacitor starts discharging through the inductor and discharges as long as a potential difference exists between the two capacitor plates. The current in the circuit is from A to B through the inductor. The potential difference across the capacitor is equal to that across the inductor. Gradually, the capacitor discharges and the potential difference between the plates as well as that across the inductor becomes zero. During the time interval, when the potential difference reduces from maximum to minimum, there is an induced EMF, which opposes the passing current in the inductor. Now, the magnetic field around the inductor starts decreasing, and this induces a current from B to A in the circuit according to Lenz's law. This induced current in the circuit, which is from plate B to plate A, charges the capacitor in the opposite sense, with plate B now positive and plate A negative. This induced current exists as long as the magnetic field exists around the inductor. By the time the magnetic field reduces to zero, the capacitor becomes fully charged. The capacitor again starts discharging, but now the current in the circuit is from plate B to plate A. This builds up the magnetic field in the inductor, but this time the polarity is reversed. Gradually, the capacitor discharges fully, and the magnetic field around the conductor grows to its strongest. Again, the magnetic field around the inductor starts decreasing, this time inducing a current in the opposite direction. This occurs until the magnetic field exists around the inductor. By this time, however, the capacitor returns to its original, fully charged state, with plate A positively charged and plate B negatively charged. Thus, we observe that the capacitor's charging and discharging is oscillatory in nature. Now, let us obtain an expression for the natural frequency of these oscillations in the LC circuit. Let Qm denote the maximum charge on the capacitor at time t equal to 0. At this instance, the current in the circuit and the induced EMF across the inductor are equal to 0. If Q is the charge on the capacitor and I is the current in the circuit at a time t, then the potential difference across the capacitor is the ratio of Q to C, where C is its capacitance. The induced EMF across the inductor is L di by dt. By applying Kirchhoff's law for the circuit, we get Q by C minus L di by dt is equal to 0. Let this be equation 1. As the charge Q on the capacitor decreases, the current in the circuit dQ by dt becomes negative. Equation 1 now becomes Q by C minus LD by dt of minus dQ by dt is equal to 0. This can be written as d square Q by dt square plus Q by LC is equal to 0. Let this be equation 2. We learnt earlier that the equation of motion for a particle of mass m in simple harmonic motion along the x-axis with a natural angular frequency omega naught is d square x by dt square plus omega naught square x is equal to 0. Let this be equation 3. Here, the natural angular frequency omega naught is equal to the square root of k by m, where k is the force constant for simple harmonic motion. Equation 2 is observed to be similar to equation 3. Comparing equations 2 and 3, we have the natural frequency omega naught of LC oscillations in the circuit equal to 1 by square root of LC. We know that in equation 3, the displacement x is expressed as a cos omega naught t plus phi, where phi is the phase difference and a is the amplitude of oscillations. Similarly, for equation 2, the charge q can be expressed as q is equal to qm cos omega naught t plus phi, where qm is the maximum charge on the capacitor. Let this be equation 4. At time t equal to 0, the charge q on the capacitor has the maximum value qm, which means that the value of the cos phi has to be 1, and hence phi has to be 0. Hence, equation 4 now becomes q is equal to qm cos omega naught t. Let this be equation 5. As the capacitor gets discharged with time, we get current I is equal to minus dq by dt. Substituting the expression for charge from equation 5 and simplifying, we get I is equal to Im sin omega naught t, where Im is equal to omega naught into qm. Let this be equation 6. Now let us analyze the LC oscillations from an energy point of view. At any instance, the energy stored in the capacitor U is equal to Q square by 2C, and the energy stored in the inductor U dash is equal to half Li square. From our previous analysis, we know that at any given time t, the charge Q is equal to Qm cos omega naught t. The current I is equal to Im sin omega naught t, where Im is equal to omega naught Qm, and omega naught is equal to the square root of 1 by Lc. Rearranging omega naught in the expression, we get L is equal to 1 by omega naught square C. The total energy, U total of the circuit, is the sum of the energy stored in the capacitor and the energy stored in the inductor. Thus, U total is equal to Q square by 2C plus half Li square. substituting the values of I and Q in this expression and simplifying. We get U total is equal to Qm square by 2C. This expression of total energy is equal to the energy stored in the capacitor when it is fully charged, which was the initial stage. Thus, the total energy in an LC circuit is always a constant. This also holds good as no external force acts on the system. Hence, this oscillation is self-sustained. We also observe that LC oscillations are very similar to the mechanical oscillations of a body in simple harmonic motion. In the case of a spring, when the spring is initially in an elongated position, all the energy of the system is in the form of potential energy. When the spring is released and it reaches the mean position, this potential energy in the system is converted completely into kinetic energy. When the spring goes to the other extreme, the kinetic energy in the system is again converted back into potential energy for the spring. In a similar manner, in LC oscillations, the energy oscillates between the electric field due to the capacitor and magnetic field due to the inductor. These LC oscillations sustain infinitely if all the elements in the circuit are ideal in nature. That is, the inductor has zero resistance and the capacitor is characterized by a single constant value called capacitance. However, in a practical situation, this is not true. Actually, the inductor also has some resistance, which leads to the damping of these oscillations. Similarly, neglecting the radiations emitted by the system also renders this analysis quite unrealistic. From our discussion of LC oscillations, we can draw the following analogies between a mechanical and an electrical system. We see that the inductance L is similar to mass. The value of 1 by C is similar to force constant K. Force constant K is the restoring force per unit displacement, whereas 1 by C is the value of the potential difference required to store unit charge. Charge Q is analogous to displacement x, which implies current I is analogous to velocity v. The total energy in both systems remains constant or is conserved. The effect of damping on the LC oscillations can be compared to that of a simple harmonic oscillator. A transformer is a device used to increase or decrease the voltage of an alternating current. It is used in power transmission to reduce the power losses and to increase the efficiency of power supply. Transformers work on the principle of mutual induction. According to the principle of mutual induction, when two coils are placed close to each other and if one of the coil carries a time-varying current, a current is induced in the other coil. A transformer comprises of two coils, C1 and C2, insulated from each other. These coils are wound over a soft iron core. The soft iron core is provided to increase the magnetic flux through the coils and to provide a medium through which all the magnetic flux through the primary coil also passes through the secondary coil. This increases the mutual inductance of the two coils as more flux from the first coil now passes through the second coil. If the time-varying magnetic flux produced by coil C1 passes through the other coil C2, an EMF E is induced in coil C2. The EMF induced in the coil C2 is equal to minus M di by dt, where di by dt is the rate of change of current in the coil C1 and M is the mutual inductance of the coils. The negative sign here indicates the direction in accordance with Lenz's law. The coil C1, at which input voltage is applied, is called the primary coil, and the coil C2, at which output voltage is obtained, is called the secondary coil. Let the number of turns in these coils be Np and Ns respectively. Let us consider the case of an ideal transformer where the primary coil has negligible resistance and all the magnetic flux in the core links both the primary and the secondary windings. In such a case, the energy in the transformer and the core are zero. Then, due to mutual induction, the induced EMF or voltage in the secondary coil ES is directly proportional to the number of turns Ns in it. Then, according to the principle of mutual induction, the EMF Es is equal to minus Ns into d phi by dt, where d phi by dt is the rate of change of the magnetic flux linked with the secondary coil. The minus sign is in accordance with Lenz's law. The alternating flux phi also induces an EMF referred to as the back EMF in the primary coil due to self-induction. This EMF, EP, is proportional to the number of the turns NP in the primary coil. This back EMF EP is equal to minus NP into d phi by dt, where d phi by dt is the rate of change of the magnetic flux linked with the primary coil. The minus sign is in accordance with Lenz's law. For an ideal transformer, the primary coil has zero or negligible resistance. Therefore, the induced EMF EP is equal to the voltage across the primary VP. Hence, we get Vp is equal to minus Np into d phi by dt. Let this be equation 1. If the current taken from the secondary coil is small, as it is an open circuit, then, to a good approximation, we get induced EMF Es equal to voltage across the secondary coil Vs. Hence, we have Vs is equal to minus Ns into d phi by dt. Let this be equation 2. Dividing equation 2 by 1 and simplifying, we get Vs by Vp equal to Ns by Np. Let this be equation 3. Thus, we observe that the ratio of the voltage across the secondary coil to that across the primary coil of a transformer is the same as the ratio of the number of turns in the secondary coil to that in the primary coil, respectively. Assuming the transformer to be 100% efficient, that is, there are no energy losses, then the input power is equal to the output power. This is a good approximation, since a well-designed transformer may have an efficiency of more than 95%. 100% efficiency is not practically possible because of various losses. We know that power P is the product of the current I and the voltage V. Hence, we get P is equal to IV. Now, for an ideal transformer, we have power in the primary coil, PP, is equal to power in the secondary coil, PS. Let this be equation 4. This can be written as IP into VP is equal to IS into VS. Or VS by VP is equal to IP by IS. Let this be equation 5. From equations 3 and 5, we get Vs by Vp is equal to Ip by Is is equal to Ns by Np. Let this be equation 6. This shows that the current in the coils is inversely proportional to the number of turns in the coil. Since I and V both oscillate with the same frequency as the AC source, equation 6 also gives the ratio of the amplitudes or RMS values of the corresponding quantities. Now, we can write the voltage and current in the secondary coil in terms of the voltage and current in the primary coil as shown. Let these be equations 7 and 8 respectively. If the secondary coil has a greater number of turns than the primary, the voltage is stepped up. That is, output voltage is higher than the input voltage. This type of transformer is called a step-up transformer. In this type of a transformer, there is less current in the secondary coil than in the primary coil. For example, if the primary coil of a transformer has 100 turns and the secondary has 200 turns, Ns by Np is equal to 2 and Np by Ns is equal to half. Thus, a 220 volt input voltage Vp at input current Ip of 10 ampere gives an output voltage Vs of 440 volt. In other words, it is stepped up to 440 volt output at a current Is equal to 5 ampere. Conversely, if the secondary coil has lesser turns than the primary coil, the transformer is called a step-down transformer. Output voltage is lesser than the input voltage. That is, the voltage is stepped down or reduced and the current is increased. For example, if the primary coil of a transformer has 200 turns and the secondary has 100 turns, Ns by Np is equal to half and Np by Ns is equal to 2. Thus, a 220 volt input voltage Vp at input current Ip of 10 ampere gives an output voltage Vs of 110 volt. That is, a step down to 110 volt output at a current Is equal to 20 ampere. These equations apply only to ideal transformers as we assumed. However, in practical situations, all transformers incur small energy losses due to various factors such as flux leakage, resistance of winding wires, eddy currents, and hysteresis. Flux leakage can never be completely eliminated, as not all the flux due to primary passes through the secondary due to poor design of the core or the air gaps in the core. To minimize the flux leakage, the primary and the secondary coils are wound one over the other. as the wires used for the windings have some internal resistance. Some energy is lost due to heat produced in the wire whenever a current passes through them. In high current, low voltage windings, this loss can be minimized by using thick wires. Due to changing magnetic flux in conductors, induced currents known as eddy currents are produced in them. The alternating magnetic flux induces eddy currents in the iron core. The eddy current in these closed loops results in generation of heat and loss of energy. This effect can be reduced by having a laminated core. The alternating magnetic field repeatedly results in the reversal of the magnetization of the core, which consumes some energy due to heating of the core. This is called hysteresis loss. This loss can be minimized by using a magnetic material which has a low hysteresis loss. For transmitting electricity over long distances, we use transformers. First, we use a step-up transformer to increase the voltage and consequently decrease the current in the transmission lines. This reduces the loss of energy as heat. Voltages are then stepped down at various substations and utility poles before it reaches our homes in the range of 220 to 240 volt. There is a practical upper limit to the voltages we can use for transmitting the electrical energy through the transmission lines. Excessive voltages can ionize the air around the transmission lines. This in turn can create a conducting path to the ground or other objects near it, and also can possibly cause damage to life and property in its vicinity. Hence, long strings of insulators are used to keep the transmission lines away from the towers supporting them, and insulators are also used to maintain separation between the wires.